Okay, there's just one problem with that last video. We were talking about how much CO2, right? And we said, well, here's the problem right here. Who on earth is going to go out and barbecue when it's that cold outside? Not me, not ever. Well, maybe I would. I don't know. I really do like barbecues. But you're probably more likely to, barbecue on a nice warm day. So let's take a look at the temperature here. And because I'm feeling lazy, I'm going to say, hey Google, what do you know? Let's say it's nice hot 90 degrees Fahrenheit. Alright, so yes, I'm still in the US and I still have to do this sort of thing. 32.222. Okay? I don't know why I copied that, I'm just going to write it out. So what if it were warmer? 32.2, who records like that? 32 degrees Celsius. Okay? What if that's how warm we're outside and you're having your barbecue? Would the volume of this gas, these 3 moles of carbon dioxide, stay the same? Well, I think you can think about that. Probably not, right? You put more energy into the system, and if this is this balloon you're filling with carbon dioxide that you're somehow trapping from the barbecue, that's a step I didn't think about earlier. The more energy I pump into it, these little particles of CO2 are going to be bouncing off the edges even harder, right? Just like if somebody's on a swing and you push them harder, they go further and further and further. The same thing's going to happen, and if that were in a balloon, it would get bigger. Okay, so we can expect that if we put more energy into the system, that it's going to result in an increase in size of the balloon in this case. There's a more formal way of talking about that, but I'm not worried about it now. Okay, so what I want to do is say, I understand that if I have a volume of 67.2 liters of CO2, I know that comes out, or I know that that's equivalent with a temperature of 273 degrees, or yes, that was right, 273 degrees Kelvin. Or actually, we just say 273 Kelvin, you know, write degrees, remember? Doug, that's me. Okay, so anyway, what I want to do is take advantage of a nifty little ratio here. And I want to make sure I get this right. But yes, okay, Charles' law. I want to attribute, whatever, the right person. I'm going to say volume 1, that's this guy over here, is to temperature 1, as volume 2 is to temperature 2. In other words, if I know the volume of the gas to begin with, and I know the temperature at the time I took that little picture, that snapshot, then I can get to what it would be at any temperature, or I can see what temperature it would have to be to get to any other volume. So what I'm going to do is say that a lot. What I'm going to do. It's getting quite tedious for me. Alright, so what I'm going to do is going to look over here and say, how many liters is that on a day like today, where it's actually hotter than that today, where it's 32 degrees Celsius. Okay, well, what's the first thing I want to do here? Well, this isn't going to work, right, because these units don't match, so I need to do some quick math here. I'm going to say 273, and I'm not going to worry about the decimal for right now, 5. That's going to be 0. That's going to be 305 Kelvin. So I'm going to scratch that out right now, 305 Kelvin. Okay, and now it's easy, right? This is just algebra. Aren't you glad you're at a point where you can say it's just algebra? Do you remember, like, actually, no, I don't. It's been a long time, but I'm pretty sure algebra didn't bother me that bad in junior high. So what I'm going to say is L, and really that shouldn't have been an L, that should have been a volume, right? So let's do it right. So 273 K times the volume is equal to 305 K times 60, let me give you a I was going to run out of space there. 60, I goofed. That's not 60. I'm just making things up. Which is great for creative writing, not so good for chemistry. Okay, 67.2 liters. Okay, and come in here and I say, well, before I do anything, I can say that these kelvins go away, and that should happen, right? Because I'm not concerned with the temperature, and I don't want an answer that ends up with that in it. So here we go. I'm going to turn on my calculator here, and I had the answer in there already. Oh well, 67.2, right? 67.2 liters. Well, and multiply that by 305, okay, and then divide by 273. So the answer is, on a hot day like today, the volume of that CO2, if it were a balloon in the same number of moles of gas, the volume 2 would be equal to 75.1 liters. Now let's see if that makes sense for what we said, because before we said that, and I think you'll see it does, that at 0, that volume was only going to be 67.2 liters, and now that it's well, hot outside, the gas expands to fill a greater volume, 75 liters, and that's exactly what we'd expect. Thanks. Bye.